predict, will this student pass this course? We want to be able to do this at the university-wide level, so we don't have to train individual models for each course. Next. Placing where we're at in the machine learning world, there's three main types of ML problems. The first of which is supervised learning, which is regression or classification problems where we know the right labels for the data. Next is unsupervised learning, where these are clustering and association problems where we don't know the right labels, but we'd like to figure those out. And then finally, reinforcement learning, which is sequential decision-making where we figure out the right labels or the best sequence of decisions that can solve a problem using the data. Next, Ross. So our problem fits squarely in supervised learning. It's a classification problem where we have training data that we'd like to fit a model to, and then be able to predict on new students in a new semester. Next. So there's a variety of methods that could be used in this space, starting with some statistical or simple machine learning approaches like logistic regression or penalized logistic regression, as well as the simple ML approaches like decision trees or k-nearest neighbors. Then there's also some more advanced machine learning approaches, such as random forests, gradient boosted machines, and neural networks. Deciding on which of these approaches to use, you need to consider a variety of factors. So we thought of implementation or ease of implementation, potential scalability, interpretability, and performance. So before I highlight our chosen approach, I just want to dive a little bit further into those considerations. So looking at this plot, on the Y or on the X-axis, I have accuracy. And I'm specifically talking about large data set accuracy, where some of these flexible approaches are really going to shine. And then on the Y-axis, I have interpretability, or really also interpretability and ease of interpretation if someone was going to implement this sort of thing in R or Python. Next, Ross. So starting in the upper left-hand corner with logistic regression, this is a method that's probably going to work really well if we were in a small data situation. But in this sense, since we have a lot of data, we don't want to have any a priori enforcement of the type of relationships between our input variables and our output variables. We also don't have an independence assumption between our rows, so we're going to admit that as being under consideration. On the other end of the extreme, there's GBMs, random forests, and neural networks. These tend to provide the best performance as long as you have a large enough data set because they can fit these flexible relationships. And so that's our chosen approach. But now the question is really, how can we lower that barrier for implementation, and how can you interpret a model like this? Next, Ross. And so luckily for us, there's Google AutoML, which Kyle's going to dig more into for us, but that lowers this usability barrier and also offers a variety of tools for model interpretation as well as prediction explainability. All right, I'm going to turn it over to Kyle to talk a little more about Google AutoML as well as the other tools that were involved.
All right, thanks, Nick. So I'm Kyle Unruh. I'm the data solutions architect for Unizin. I work very closely with UDP, and I've really enjoyed the opportunity to work with the Iowa team on this project. Ross and team started this project and then kind of brought me in to do deeper integrations with UDP. And it's been a really exciting journey to get to this point and share it with you all today. So yeah, as Nick mentioned, I'm going to kind of go under the hood and talk about the different tools and data and how we took kind of raw teaching and learning data and fed it through all of these tools and techniques to actually get predictions out for student success. So we're going to start with three main components. The first is the Unizin data platform. This is where all of the data live. And the Unizin data platform is a single data warehouse that aggregates and unifies all data about learners, learning environments, and learning processes. It takes the plethora of tools that universities have to capture a robust learning experience, transforms that data based on standards-based approaches, and stores it all in one place to act as a single entry point for any type of project or application. The digital learning scorecard, which we're talking about today, is one of those applications. As I mentioned, it's standards-based. So we have a in-house Unizin standard called the Unizin Common Data Model that we adhere to, as well as an external standard called the IMS Global Caliper Standard. These two in concert are what we use to transform data into common ways and ensure their quality, and to make analysis and research easier on that data. And as Ross and Nick have alluded to before, it's all built on the Google Cloud, so it's cloud first. There's no requirement for the University of Iowa to have any infrastructure of their own to utilize the UDP. It's all cloud first, and it scales as their data scales, which makes a lot of these types of projects more accessible and approachable. The second tool we use is Google BigQuery, and this is a serverless scalable data warehouse that's on Google Cloud. So it sits right next to where we store the data on Google Cloud and allows us to have quick performance writing queries on large data sets, so terabytes of data. One part of the UDP we call the event store, and the event store is it follows the IMS Global Caliper Standard, and it is the sequence of events that happen in any learning tool. So it's every click that happens, every page that's viewed, every tool that's launched. We capture those events in one table, and it can be well over a terabyte. I think Iowa's event store to date, since the UDP is turned on, is over 6 terabytes. So we needed to have a tool that was able, we were able to write queries that were understandable, so writing SQL queries, but also have it perform in a cost-effective and in a quick way. So BigQuery was really essential for us to take the UDP data and transform it into a way that we wanted to answer our modeling question. And then the last tool that we use, as Nick alluded to, is Google AutoML. And this is on Google Cloud yet again, and it's Google's supervised learning service for structured tabular data. And structured tabular data is the form in which the UDP is delivered. So connecting data through BigQuery and into AutoML made a lot of sense for us. It's a very streamlined pipeline in that way. It integrates directly with BigQuery, so all you need to do is define tables in BigQuery that are SQL defined tables, and you can connect that as a training set into AutoML, and then let AutoML do the rest given parameters and specifications. And again, similar to all the other Google Cloud resources, it scales automatically to fit the problem. So as you have more resources and as you have more data that's coming into the UDP and coming into AutoML, in the background, Google AutoML will spin up more resources and spin up more nodes to do the analysis and train the neural network. So again, it's not on Iowa or any other university to have their own infrastructure to do these models. No reliance on supercomputers or a lot of heavy equipment to get this done. So these are the 3 main components. And we want to dive a little bit more into why we chose AutoML, given there are many options. Even on Google Cloud, there are more options than just AutoML to do this. So I really see this along, there are 4 main benefits. The first is model selection, or another way to perhaps say that is lack of model selection. What AutoML does is it spins up resources in the background and it trains a neural network for you. It does the deep learning. You don't have to hand train or hand pick anything. Instead, what you're able to do is you're able to focus on the data that's coming into the model and focusing on optimization parameters for the output of the model. So that's really where we spent most of our time preparing this project, was getting the data right and establishing our target columns and ensuring the quality of that data. And we spent very little time actually figuring out what model to train, because AutoML kind of does that for us. So it abstracts that away and allows us to really focus on other aspects of the modeling process. The second benefit, as we see it, is approachability. So you don't really need any prior machine learning experience to get the most out of AutoML. And AutoML, once a model is trained, it gives you a lot of resources and a lot of output to explain why it makes predictions. And it gives confidence levels alongside each of those predictions, so you know how much to trust that prediction. It's not a black box model that you don't understand. And the approachability of AutoML allows teams that have perhaps younger experience with machine learning or no experience with machine learning lets them kind of interact with predictive models in a way that lowers that barrier. So we really like that part of AutoML, especially for operationalizing and scaling a solution like this. Third, operationalizing. So AutoML has, without going into too much detail about how predictions are kind of spit out of AutoML, there's live predictions and there are batch predictions. And so once you have a model, you can then prepare a new set of data. So perhaps if we're training through spring 2021, but we want to get predictions for fall students, all we have to do is take data for fall 2021, structure it in a way that AutoML expects for the model, and then we just give that data to the model. There's no extra massaging of data. There's no extra retraining that has to happen. AutoML supports frequent new predictions whenever new data is surfaced, either in a batch format or through live streaming if needed. So there's a lot of flexibility there to really match the model to your end applications and not the other way around. Your end applications can kind of stay as is, and you can integrate AutoML as you see fit. And then the last benefit for why we chose AutoML is scalability. This plays on the standards-based approach of the UDP as well. All of the queries that we wrote that work on Iowa's data today can be lifted and shifted to any other school that uses the UDP. Every school that has UDP has equal access to AutoML. So all we have to do is repoint those queries from pointing to Iowa's data to pointing to another institution's data. And that institution can then start having a digital learning scorecard model, just like Iowa has. So those are the four reasons why we chose AutoML specifically for this application. And then the last I'm going to talk about in terms of tools is just the total pipeline, how we got from data all the way through to a model. So we start with the UDP data, which is the raw UDP data that lives in Google Cloud. And the first thing we did is we wrote SQL queries in BigQuery to create what we call features. These are the learning attributes of students and the behaviors that we want to capture that we think could be predictive of success. We store each feature in a column, and then that feature set is split into a training set and a test set. And next transition. The training set is what we feed into AutoML, where we have a target column, which is the success of the student, whether the student passed or did not pass, plus all the feature columns. And then what we're able to do once we have that model trained is we can take a test set, which is independent of the model. And next transition, feed that test set into the model, and then we're able to get predictions. And the way that AutoML and BigQuery interact is you feed data from BigQuery into AutoML, and the predictions get spit from AutoML back into BigQuery. So it's really utilizing and getting the most out of these tools. And once we have these predictions on students, we're able to finally, last transition, connect those predictions, which are just tables in BigQuery, to any report, dashboard, or application that either currently exists or could be created new. But the predictions just live as a flat table in BigQuery and is really, really easily connected as needed. So we thought that this framework really nicely integrates into how Iowa likes to use data and how Iowa is currently using the UDP without adding too much extra complication on top. As we go forward in the presentation, I'm going to spend a little bit more time on the features. And then Ross at the end is going to spend a lot more time on kind of the dashboard applications and kind of next steps of that. So I'm going to spend more on the beginning of the pipeline, and Ross is going to spend more time at the other end. So a little bit about our model features. We were very intentional up front on the types of features we wanted to include. Specifically, we were very explicit about including only in-term features. And what we mean by in-term features is behaviors that start at the beginning of a term. We really wanted to see how much current activity is predictive of student success. So we exclude features such as like cumulative GPA. We're not looking at the past performance of a student in order to predict their current performance. If you're familiar with some student success predictors out there in literature, you're probably familiar that cumulative GPA is a heavily correlated predictor. And we're not saying that cumulative GPA should never be used or past term predictors should never be used, but for this instance, we really wanted to start with a clean slate each term for a student and see how much in-term behavior influences their success. So we kind of see digital learning scorecard as a complement to those other models, not necessarily a different way to do it, but it's just trying to isolate those interim features. And in terms of those interim features, we have temporal natures to those features. So we have a cutoff at 6 weeks in the term. You could have a cutoff at any number of weeks. That's why we say in weeks. But after a certain amount of time in the term, we cut off the data that we're collecting, and we try to predict the success, the pass or not pass of a student at the end of the term. And we are explicit about setting that for this model at 6 weeks, but any number of weeks could be used. And we also really wanted to, if you go back a slide, we also really wanted to capture the early enrollments of students with little or no historical data. Some of the other models that use heavy historic data, like cumulative GPA, don't perform well on early enrollment students. And we know that success of freshman students, especially entry-level students, is really key in terms of persistence and retention. So a model that only uses interim features doesn't have that limitation of waiting a couple terms before it's useful. And in terms of the data, how we've split the data, we have training data, which is any data before spring of 2021. And we're using our test data of the current term, spring 2021. Next slide. So we group our features along two main different types. We call them learning context features and student activity features. I'll start with the ones on the left, learning context features, and these are intentionally light because we want to focus on student activity, but learning happens within a context. So there are a few different attributes that we think could contribute to student success or failure, depending particularly on historic grade distributions. The first is the term type. We think that whether or not it's a fall, summer, or spring term could be an influencing factor on how a student does. There are different courses that are offered, different instruction periods, different course meeting patterns that could affect whether or not a student, how a student does in a course. So we wanted to capture that given the term type. We also want to capture course subject and course levels. There's commonly in literature, we see that there can be some grade penalties in STEM courses because STEM courses have different historic grade distributions than other departments. So we wanted to capture the course subject to see if, maybe some courses in different departments are historically harder than other courses. We also wanted to capture the course level. Maybe perhaps the distribution of freshman courses for student success is different than sophomore, junior, and senior. So those are the three learning context features, which are admittedly out of the student's control, but we think could affect the model in terms of their success. Where we wanted to spend more emphasis, though, is on the student activity features. And these first ones here, everything through enrollment number, or except for enrollment number, is through week 6 of the term. Anything after week 6 is not included in the model. So we cut off at week 6. But we're capturing the number of LTI launches per person per course. We're capturing the submission behaviors of students, the number of days that they've viewed Canvas for a course, and the number of minutes they view Canvas. And these two are definitely correlated, but the view days are more so the frequency. So how regularly or how often a student is viewing their Canvas course materials, and minutes in Canvas is kind of the quantity, like how much time are they actually spending in Canvas. So we wanted to capture both aspects of that behavior. The learning activity score, so how they're doing so far on assignments, and then the discussion entries. Are they interacting with other students in Canvas along discussion entries? Are they engaging in that way? And then the last student activity feature that we include is what we call enrollment number. So if a student has previously dropped a course and then this is their second or third time taking the course, we also wanted to capture that as well. Because that could affect how a student does or how a student approaches a course if it's a multiple time that they've taken it. And then the last column, the last feature, is really our target, and we're calling this past course. And so we've coded the A's through F's, the passes, the successes, the unsatisfactories, the withdrawals, everything into a past course variable, which is either a student has passed or a student has not passed. So we consider this a binary classification model. And what AutoML is doing is it's taking all of these feature columns and then trying to predict whether it's going to be a 0 or 1 for this past course. And that's how we're determining the performance of the model. So with that, I will hand it over to G to explain how our model is evaluated.
Thanks, Kyle. Hi, I'm Ji Guo. I'm a learning analytics specialist at University of Iowa, and I'm also a research methodologist. So what we are doing in this model is so we try to find the best model we can find. When I say best model, that doesn't mean we want to find the highest accuracy model. We also want to find the most the best fit model for the operation, university operation, and also we want to find the best model for the explainability, because we try to avoid any type of garbage in, garbage out result. So we want our model both be meaningful and useful. This is the our model performance. We can see the accuracy is 88.8%. Well, based on the features we specifically selected for this model, I think this accuracy is pretty well, but accuracy is good. Well, that's only one part. In addition to the accuracy, I want to talk a little bit about the false positive rate, which is you can look at the confusion matrix. On the right side, you can see prediction, that part, so not passed, and the true labels with pass, that's only 10%. This is relatively low, because a lot of times, even some models that has a high accuracy rate, even like a 90%, 95%, their false positive rate is high. False positive rate is very important in our model selection and also in our evaluations, because our audience is the advisors, and in order to support our advisor to use this model and support those instructor, support those students, university have to devote some resources, right? So 10%, if our model predicts a student are going to not pass, have a not pass status, but they are actually going to pass, well, that's the not accurate part, but the university will have to devote more resources to those students to help them, no matter advisors, instructors, or even those supplemental learning professionals. They have to devote resources to that part. But if the rate is high, that means university is going to waste some resources on those students, because some of them are going to pass. It's they are labeled not pass. That's because that's a model prediction. So that's why we specifically care about that false positive rate. So this is in our model, it's 10%. That means universities can actually devote some resources to help those students to succeed without wasting much of the resources. Please go to the next one. Yeah. Now we are looking at the explainability of this model. So you can see in this model there, from upper to bottom, you're gonna see different features, and you're gonna see some numbers associated to those features. Just consider those numbers as coefficients. That is the importance of these features. That is also the variance explained by this part. So you can see in this model, the current best model we have a course subject as the most important part. Course subject actually is not only the course subject, it is the context part that explains the difficulty of the difficulty of this course. Think about this. So if you're in a PE course, and also compare if you're in a mathematical course, or if you're in a social science course, the difficulty level may vary. And also we can see view days, learning activity scores, course level, also minutes spent in Canvas, and also your submission. Now I want you guys think about it this way. We actually we show this one to advisors. We want to give advisors a very positive explanation that they can talk to their students. For example, course subject and course level, whether the course has the LTI lunches, those are all context part. The course design or the course context, those are extrinsic reasons that impact the students' pass or not pass rate, especially in prediction. Then you look at the view days, week 1, learning minutes, week 6, view days, week 6, submissions. Those are actually student behaviors. Do they log into Canvas? Do they devote their time in Canvas? Do they do submissions in Canvas? Those are all the student behavior part. And also you also see learning activity scores week 1, learning activity scores week 6. They are actually student performance based on their past engagement, based on their past behaviors. So then when we want to explain this model to advisors so they can explain to their students, we want to encourage them. We want them to encourage students. See, there are some course subject, course context, variables that we cannot control. You already enrolled in this course. That's extrinsic reasons. There's no way we can control that. But look at that. Even we cannot control that. There are a lot of things that is you can do, like logging Canvas site. Also, you submit assignments, you devote your time in learning, you actually engage in those course content. Engaging this course content, so you are less likely to be labeled to fail the course. You will not be labeled as non-pass in the model. So when communicated, you can say you will pass the course, you will succeed in the course. Also, you can see even we have some learning activity scores. Think about this. Even there are some past performance that is based on your past engagement. That's okay. Oh, I understand that you probably did not engage that well in the past, but think about those behavior, variables, the behavioral features. If you engage more in the future, you're more likely to succeed in this course. You're more likely to get a passing grade in this course. You are more likely to pass this course. That's why we actually picked this model, because it gives not only gives advisors some context to say why students why students pass or not pass. It also gives the advisors some ideas how to explain those type of things in practical, with practical consideration to students, and encourage students, hey, you are having this difficulty because of this, and then if you do something, there is a way you will succeed in the course. Next slide, please. Okay, so I know there might be some considerations. Might be some considerations about, why course subject is important, or why the course level is important, something, because that's the context. Learning actually occurred in certain context. Like me, if I'm a motivated person, but I might be struggle in some like American literature courses because of the lack of because of course design, because of the lack of language skills, because of the the background knowledge in those history or culture, but I might be doing well in the STEM courses because I have a background in statistics. So look at this is actually the comparison between learning context and student activities. Although you see the top important part is a core subject, you see those context part. Think of the learning context actually contribute just a 1/5 portion of students succeed, but the student activities, in other words, your behaviors, your engagement, and your performance and evaluation based on your past behaviors and performance and their engagement, they are more important to devote to determine whether a student is going to pass or not a pass. Then that also makes this model a pretty good one. And it's not it has some practical applications to our current context, especially to the university environment. Now I'm going to hand it back to Ross. We're going to talk about the practice.
Okay, thanks, G. And I think, G's kind of talked about a lot of what we're going to cover here, but, once we're labeling students at a pretty high rate, you can see that our model here at week 6, being able to label at close to 90%, we want to think about how this actually gets used on campus. So how can advisors actually put this into work? And we have some mock-ups of what we think that might look like. So in evaluating this model, we can talk about labeling a student. So we're going to say, for this student, we're going to say that they are predicted to pass this course. I don't think it's good enough to say just that we're going to label them as pass. I think we need to say at what confidence we're making this prediction. So confidence is 76%. And then why this prediction is reliable. Well, we can see that this student spends enough time in Canvas, is doing well on graded assignments, and has participated in discussions. And then you can actually see visually here what parts of our model made up the biggest parts or the smallest parts of this prediction. And I think you can easily see the inverse of this type of prediction as well. You could say that the student is predicted to not pass this course. Well, the student is not spending enough time in Canvas, is not doing well on graded assignments, and has not participated in discussions on pace with his classmates. I think those are really important and easy conversations that advisors or other student success individuals could have with students to really make this an effective approach. I saw one comment in the chat that talked about, well, are we ignoring some features? And yes, intentionally, if we wanted to just have the model that says that most accurately predicted is a student going to pass or fail, we would include lots of additional features about course design, about a student's prior learning outcomes. All of those would be highly predictive to if a student passed or failed a course or not. And I think that what we were looking to do with this particular model is speak to what is this student doing in this particular semester, to say that, if a student, because I think with GPA predictions, we'll already have a really good idea of, based on their prior learning outcomes, how are they predicted to do in this semester? But we really want to see how we can target advisors' time the best. So if you can look at this as an example, this first row is a student that we would say is someone that advisors need to target very quickly in saying that they are someone that needs an intervention. So they have a low prediction overall, and they also have a low digital learning scorecard score for this semester. As where in another student, they might be a lower prediction in terms of digital learning activity, but they have a higher GPA prediction. So this might be a little bit of a lower priority intervention with a student. So that was just some thoughts in terms of how we could see this being used by advisors or by actual student success teams at universities. And then I want to talk a little bit more about some of the future possibilities that we have as a consortium and as with this project. So I think with more learning tools, as we push more data to the UDP, that there's lots that we can do in terms of building more predictive features or additionally predictive features. There's other things that we can do in terms of building out cohorts. So our current model is just based, it's all trained on undergrad data. But building out some of those based more on like, is this a online only course or a in-person lecture lab course, that those would probably have very specific tool usage, and that could lead to some good cohorting and better models in the future. And then like I talked about on the slide before is combining with other models to know when and how to do interventions. And then talking about a call to action, I think the promise of Unizin and how we've built this model out is to work on validating and improving this model with other institutions. So we would really like to see if other institutions can reproduce our work. Can we create models that label at an equal rate with other schools? And I also think that it would be a very interesting multi-institutional model. So since all this data, we don't have any identifiable data here. So there's no even student IDs aren't even important here. We just need their digital scores along with a passed or failed grade. And if we combine those into one data store and train a model based on that, it would be very interesting to see what kind of model we got. Like Nick talked about with these neural nets, they tend to perform really well on bigger data sets. So the more and more rows that we add to a training set, the better model we would probably get based on that. And then I think the bigger question then is to see is, can we actually use this modeling to actively intervene with students and improve their outcomes? I think that's hopefully a promise that we have with projects like this, and really a promise that we were looking for as schools that joined Unizin. And with that, I will jump to questions. And Kyle, were there some that you were jumping in on here already in the chat?
Yeah, so there are a handful of questions. I think we addressed a couple. Some we addressed in the chat, and some we addressed kind of just verbally. So I'm gonna, if I skip your question, please, all caps in the chat, call me out so we can come back to it. So I think the first question was, couldn't you be missing in terms of figuring out the interactions between GPA plus historical features and the ones that are term related? Ross, I think you mentioned that during your part. So in the interest of time, Patricia, if we want to come back to it, let me know, but I think that was addressed. Our predictions applied only to course subjects. So we would love to split the data along cohort lines, identifying perhaps early enrollment students, or identifying just STEM students, or identifying other ways to split the data. We found we needed more rows using the AutoML approach in order to get good performing models. Whenever we dissected our data set along those lines, we didn't get anything that performed really well. So as Ross mentioned during the kind of next steps, we'd love to get more data, whether that's in a multi-institutional, depersonalized, de-identified way, or if it's by just waiting for more terms of data to come through so we can do those splits. But yeah, we would love to get finer tuned models, or a model per cohort. That would be great. So Jose, I see a question here. Model predictions can be evaluated by looking at the confusion matrix per week during the first 6 weeks. I'm assuming your question is, do we have confusion matrices for each week? And the answer to that is, and correct me guys if I'm wrong, but I don't think we do, because if we wanted to get a confusion matrix per week, we would have to train 6 different models. So we'd have one that ends at week 1, one that would end at week 2, one that would end at week 3. And I think that's the way that we would have to do it in AutoML in order to get that per week, right?
Yeah.
Yeah, so we could get that, but we don't have that. We chose the 6 weeks, so we have everything up to 6 weeks, but that is something that we could include. The next question I see is, are you including the course instructor as one of the features? That is an interesting feature. I don't think we are. Do you guys have any comments on that?
I think that's one that I'm a little bit too scared to introduce right now. I think that it probably is highly predictive, but probably one that would be a little bit more controversial on our campus, especially when we talk about getting adoption of this as an idea. But yeah, probably one of those contextual features that is highly predictive.
And it also just raises new modeling questions for us, like how to predict on an instructor who hasn't taught a course before. Should there be certain thresholds for you have to have taught a course a certain number of times before we start using that instructor's name as a feature?
Mm-hmm. I see a question from Matt. I understand the usefulness of some of these predictors in improving the accuracy of the model. However, I wonder if there is more work to be done here with regard to interpretability. Yeah, I totally agree. AutoML per prediction will give you a ranking list for each of the features for how it makes that prediction. But I agree there probably is more work to be done in terms of interpreting, because at least the way that I see it, interpreting a model is correlated with how well the model is trusted. We're in no way wanting to have a model that is at odds or competing with any other tool or resource or personnel that's trying to ensure student success. We want to collaborate with those groups and then with those other applications. And I think interpretability is key there.
Yeah, and Matt, your second point there about the kind of course load that a student has is a feature we've actually been looking at, that we've been working on including as part of our model, to see if that does play a factor. So far, it's been low on our feature importance, but something that we'll probably keep in there because I think it is important to recognize.
And also, Matt, you asked about the latent variable. Actually, our features are already confirmed by the covariance-based SEM models, or if if it's not confirmed over there, we will not implement over there. Now our challenge is, I know it's social science, it's a context. It's a context level, but there is a big gap between machine learning world and also social science world that we can implement latent structures into the machine learning part. We are now exploring the possibilities of using partial least square to examine the course level, and also both the course level at the university level, try to combine some variables and also extract those features into the AutoML and also the machine learning models. But that's gonna take some time. If you are interested, please give us some. If you have some ideas, feel free to share with us, because it's education, it's a social science. A lot of things are based on latent constructors, and we acknowledge that, and we are definitely going to take that into the consideration. And also, Naris asked a question: Can we small data per course or set of course to build the pilot model? Yes, that's durable, but they can. Kyle and Ross can ask about the answer about the AutoML part.
Yeah,
but if you want to looking at a non-AutoML part, like I said, partial least square SEM model would be pretty good to fit your needs, because it allows a very small sample size. A lot of statistical models doesn't do that, and it allows the non-distribution. It doesn't require any distribution, and the most important thing, you can just implement some latent structures into your prediction, which is super important.
So we have just a couple minutes left. I do want to address Jose's question about the imbalance in the data set. So you're right. We noticed that there are a lot more passes than not passes in the data set. So one of the things that you can do for AutoML is you can have a weight column assigned to each classification label. What we did is we heavily penalized the model by assigning a really high weight to the underrepresented class. We looked at doing undersampling or oversampling as another alternative, but the weight column is what we ended up going with for this model. And then the last couple, have we looked into ensemble models or stacking approaches? I don't know if you guys have a comment on that, but we've really just tried the AutoML approach first. Yeah,
I think that's something that I'm really interested in, is kind of like next steps for this project. I think that we do need more data though. So more semesters or more schools to jump in with us to really get to training sets that are going to be really good. even in these kind of examples, it's not like we have billions of rows, it's more of the hundreds of thousands. So
right. And then last, we have just 30 seconds left. Allison, did you do anything to try to clean up messy courses or exclude courses? Yeah. Oh, I see Ross has an answer there. Yeah, we excluded some 1-credit courses. We excluded some, if a course was live but didn't have any enrollments or didn't have any activity or was just kind of a stale course, yeah, we took those out. But we probably could be a little more watertight. And I think if we have more data and we split into cohorts, that's an opportunity to further have rules per cohort on what we include as a valid course for training.
Yeah.
And Sandeep asked, have you looked into ensemble models stacking approaches to accommodate it for course design and pedagogical variabilities?
We talked about that one, G.
Yes, I want to add one thing. One thing about that is we have a variety of course design and pedagogical variabilities. Based on our research, the biggest concern is not a course design or pedagogical variability. The biggest consideration right now is if something linked out of a canvas, like to peers or third-party vendors, we lose some data, and that type of data is available to that course. Our current model, we did some something to deal with the course design and pedagogical variabilities, but not that much. So if you have some input, and please contact us, we are happy to make that happen better.
Awesome. Great discussion. Thanks everybody. We really appreciate your time. We love the opportunity to present this work to you. And again, reach out to any, Ross or me, given these emails, and hope to connect with you all soon. Thank you. Bye everyone. I'm going to end the meeting.